Assalamualaikum warahmatullahi wabarakatuh. In this video, me and my friends are going to talk about static electric field. These are my group members, which is me, Hazika Nurikmah binti Marzuki, Huda binti Hasini, Nurin Inwana binti Rokim, and Siti Maisarah binti Mazlan. First of all, I am going to talk about Gauss law. Gauss law is a fundamental law in electrostatics. It tells us that the total electric flux through a closed surface depends only on the charge enclosed within that surface. Mathematically, it's written as VE equals the surface integral of E dot dA equals Q inside over epsilon naught. Here, E is the electric field, dA is a small area element on the closed surface, and C is the permittivity of free space. This law is most powerful when used with symmetric charge distributions like spheres, cylinders, or flat planes, because it simplifies the math. Remember, Gauss law only considers charges inside the surface, and it's a great shortcut for finding electric fields without needing to use Coulomb's law directly. To really understand Gauss law, it helps to visualize the electric flux. Think of electric field lines as arrows coming out of a charge. If we place a closed surface around a positive charge, field lines pass outward. That is positive flux. If the charge is negative, they point inward, which is negative flux. But here is the key idea. If the charge is outside the surface, any lines that go in will also come out. So the net flux is zero. This is why only the enclosed charge matters in Gauss law. The shape of the surface doesn't matter. It just needs to be closed. But picking a shape that matches the symmetry of the situation, like a sphere or a cylinder, makes the math much easier.
Hi everyone, I will explain briefly about electric potential. Electric potential is the word needed to move a unit charge from one point to another in an electric field. The potential difference between 2 points is given by VAB equals to VB minus VA is equal to negative integrate A to B E dot dl. This measure in volts, where 1 volt is equal to 1 joule per coulomb. Importantly, is a path independent. Only the start and end point matter. For a point charge, the potential is VR Q over 4 pi epsilon naught R. And if there are multiple charges, we use a superposition principle to sum them. Is equal to VR equal to 1 over 4 pi epsilon naught sum of I QI over R minus RI. There's a quick overview of an electric potential. Let's go through a sample problem for electric potential. We have a point charge 5 nanocoulomb located at the origin. The electric potential at point P is 0, 6, negative 8 is given as 2 volts. Now we are asked to find the potential at point A, the potential at point B, and the potential difference between A and B. To solve this problem, we use the formula for point charge potentials. Is V equal to Q over 4 pi epsilon naught R, where 1 over 4 pi epsilon naught is equal to 9 nano. For a point A, the distance from the origin is 7 meter. So VA is over 45 over 7 is equal to 6.29 volts. For point B, the distance is approximately 8.66 meter. So for VB is 45 over 8.66 is equal to 5.197 volts. And the last is the potential difference is VAB is VA minus VB. So 6.429 minus 5.197 is equal to 1.232 volts.
What is potential energy of a charge distribution? Electrostatic potential energy is the work done to assemble a group of charges from infinity into their position. It depends on the amount of charge and how far apart the charges are. The more closely packed and stronger the charges, the more energy is stored in the system. No work is needed to place the first charge, but to bring the second charge, work is done by W2 equal to Q2 dot V21, where V21 is the potential from Q1. For the third charge, W3 equal to Q3 dot V31 plus V32. The total energy is given by 1 over 2 sum of Qi Qj over 4 pi epsilon naught Rij. These sums all pairwise interaction once. Why it matters? This concept helps us calculate energy stored in systems like capacitors and charged particles. It tells us how much work we need to build a charged system, or how much energy would be released if it breaks apart. So it's useful in real-world devices and fields like electronics, physics, and chemistry.
Properties of materials. Materials can be clarified in terms of their conductivity. Conductivity is measured in ohm centimeter -1 or Siemens per meter. Metals have a very good conductors, high conductivity. Difference with insulators, which have a very poor conductors, low conductivity. While semiconductors conduct electricity better than insulator or worse than metal. Convention and conductivity current. Electric current is generally caused by the motion of electric charge. Electric current I is equal to amount of charge Q following per second. J equal to dQ over dt. If current flows through a surface area, J equal to delta I over delta S, or delta I equal to J cross delta S. Does not involve conductor. Convention also does not satisfy Ohm's law. It occurs when current flows through insulating medium, liquid, gas, vacuum. For example, a beam of electron in a vacuum tube. Consider a filament with area delta S. F equal to negative EE. Convention current density general. M over top equal to negative EE. Conduction current. A conductor has many free electrons which move when an electric field E is applied. Force on an electric. Drift velocity. U equal to E torque over ME. Electronic charge density. Rho V equal to negative NE. Conduction current density. J equal to rho V dot U equal to NE squared torque over ME equal to sigma E. Conductivity NE squared torque over M. The point form of Ohm's law, J equal to sigma E. A perfect conductor. A conductor is essential natural although it has free electron influence of external electric field. Electrons are pushed to one side and leaving equal magnitude. The electric field inside the conductor E equal to 0. The resistance of a conductor R equal to rho L over S. The electric field applied is uniform and its magnitude is given E equal to V over L. Since the conductor has a uniform cross section, J equals to I over S rearranged. The equation then we get R equal to V over I equal to R over sigma S. Resistivity of conductor rho C equal to I over sigma. Joule's law. Power. The rate of change of energy W in joule of force times velocity. Integration of rho VD VE dot U equal to integration E dot rho V U dV, or P equal to integration of E dot J dV. The power density. WP equal to dP over dV. E dot J equal to sigma modulus E squared conductor with uniform cross section dV equal to ds dl. The most common form of Joule's law is P equals to I squared R.